All right, so let's pick up where we left off last time with our discussion of intermolecular forces. These are the interactions that take place between neighboring molecules. We ranked them from the very weakest to the strongest type of intermolecular force that we see. The very weakest are what we call dispersion forces. And these arise from the temporary fluctuations in electron density in a molecule. These are the only interactions that nonpolar molecules have with their neighbors. Stronger is dipole-dipole and then hydrogen bonding. These are both available to polar molecules because polar molecules have these partial positive and partial negative ends, and they can line up next to each other. Where do we picture that? Boom. Right? In a polar molecule, you have a partial positive end and a partial negative end. So between neighboring molecules, the partial negative end of one can align itself with the partial positive end of its neighbor, forming this favorable interaction, right? Opposites attract. Hydrogen bonding is then just a special type of dipole-dipole interaction that is available to certain bonds. Oxygen-hydrogen is one of those, as well as nitrogen and hydrogen, and then fluorine and hydrogen, all of our tiny electronegative elements. And again, we form a dipole-dipole type interaction, but now that partial positive charge is on a hydrogen, which just makes it that much stronger, right? This is just like a dipole-dipole interaction, but we put it in its own separate category because it's stronger than all the other dipole-dipole interactions. And then lastly, a very specific interaction that's available to ions in polar molecules are what are called ion-dipole interactions. Very similar, except for the fact that ions have a net charge, not a partial charge associated with them. But that full charge will line itself up with the dipoles in these polar molecules here. All right, so these were these four intermolecular interactions that we talked about. Again, dispersion forces, we kind of imagine those with this little picture here. Right? These electron clouds in my atom are constantly moving about, and every once in a while there's a split second where the electron cloud of one can interact favorably with the protons in the other because this other electron cloud moved out of the way. It's going to move right back, right? This is a very fleeting interaction. But nonetheless, all molecules have electron clouds. So these dispersion forces are present in all molecules. Why did we single out nonpolar molecules? Because they're the only interaction that you see in nonpolar molecules. Polar molecules also have dispersion forces, but they have even stronger interactions, dipole-dipole and hydrogen bonding, right? Everything has dispersion. It's just polar molecules also have these even better forces available to them that nonpolar molecules don't, all right? So just to make note about our dispersion, because this is kind of a subtle point that's very important here. All right, our dispersion forces. All right, these are available to all molecules. All right, again, we're going to single out nonpolar molecules because these are the only intermolecular forces. We're going to abbreviate intermolecular forces, IMF. Available to to nonpolar molecules. Okay. All right, so in terms of like our trends of dispersion forces here, the strength of these dispersion forces increases with increasing surface area. Right? So a molecule that has a lot of surface area can form stronger dispersion forces, stronger dispersion interactions, because then there's more atoms and more electron clouds that can exhibit those little fluctuations. That is the origin of these interactions. All right? It also will increase depending on the number of electrons that an atom has. So our larger elements with more electrons will have stronger dispersion forces than our smaller elements, which have fewer electrons. All right, so the strength of these dispersion forces will increase with increasing atomic size. Or I guess let's just say atomic number. Okay, we're going to switch gears for a second and then we'll tie it back in with these intermolecular forces. We're going to talk about phase changes real quick. Okay, a phase change would be going from a solid to a liquid, or from a liquid to a gas, or vice versa. We can go from a gas to a liquid, or from a liquid to a solid. So these are what we mean by our phase changes. Changing that state of matter. So for example, if we boil water, it will become its gaseous form, steam. If we put water in the freezer, it'll turn into its solid form, ice, right? So these are these phase changes. Okay? We have certain terminology for these phase changes. What do we call it if we take ice and take it from being a solid to a liquid? What did we just do to that ice cube? We melted it, absolutely. So solid to a liquid, we call that process melting. Likewise, what do we do? What do we call it when we take the water and we put it on the stove and we make steam? Boiling. Okay, the inverse of melting, going the other direction from a liquid to a solid, is what we call freezing. And going from a gas to a liquid, taking a gas and cooling it down so that it goes into that liquid form, is what we call condensation, condensing. Okay, and we can also go, it's not something that happens all the time. There's a specific kind of feature of a molecule that would lead to this. But it's very popular in organic chemistry, so we're going to talk about going directly from a solid to a gas without passing through that liquid stage. This is what's called sublimation. You can use this to your advantage to purify certain compounds. Caffeine is a molecule that will sublimate really easily. And it's an easy way to purify that compound after you isolate it from, say, coffee or something like that. Okay? All right, so then why the heck are we talking about phase changes in the context of these intermolecular forces? Well, let's think about it real quick. If we're going to take a liquid and we're going to heat it up so that it becomes a gas, right? In the liquid phase, those neighboring molecules are right up against each other, interacting with one another very strongly through what we call these intermolecular forces. If we're going to take this thing and put it into the gas phase, we're going to break those intermolecular interactions. All right? So it turns out that the point in which a substance boils will correspond to just how strong those intermolecular forces are between neighboring molecules. All right? And it's a little bit less easy to wrap your mind around, but the same thing is true with the melting point of a substance. The stronger neighboring molecules are interacting with one another, the more energy, the more heat you have to put in to break those intermolecular interactions. All right? So we use boiling point for a liquid or a melting point for a solid as a measure of just how strong those intermolecular forces are. All right? So, that just got real loud. All right, so the temperature of these phase changes. How many millions of children just passed by here? All right, okay, so the temperature of a phase change is used as a measure of the strength of those intermolecular interactions, intermolecular forces. Okay? For solids, we would use its melting point. Okay, by melting point, I simply mean that temperature that it melts. Okay, if it melts at a specific temperature, that's also the temperature that it freezes at. So these are interchangeable with one another. We can talk about the melting point of a solid or the freezing point. That temperature is the same. All right, you will more likely hear it referred to as melting point because in practice, that's really what we do. We go into the lab, we take a little bit of that solid, we put it onto this little instrument that's going to heat it up, and we're going to watch and record the temperature at which that substance melts. And again, that temperature is proportional to just how strong those intermolecular forces are between neighboring molecules. For liquids, we would use its boiling point because again, we got that same easy experiment that we can do. It's called the boiling point. This is just the temperature at which it boils. All right, and this would be the same as that condensing point, although in practice I've literally never heard somebody use the phrase condensing point. It would be the same temperature, but again, in practice you'll hear solids being referred to by their melting point and liquids being referred to by their boiling point. Okay, and again, this is a stand-in for these intermolecular interactions here. So let's take a look at a few simple molecules and see if we can't rank these from the lowest to the highest. And we're going to look at some liquids here. So in this case, we're going to look at boiling point. All right, we want to rank from lowest to highest boiling point. All right, so what we're going to do is we're going to look at molecules that are all about the same size, but they're going to have different what are called functional groups, these different features of this molecule that interact with different intermolecular forces. So we're going to look at a few Lewis structures. Oops. All right, so we want to take these molecules here and we're going to try to rank them from the lowest to the highest boiling point here. Okay, so how are we going to do that? So first of all, when we say the lowest boiling point, right? This boiling point is a measure of just how strong those intermolecular interactions. So if it's got a low boiling point, does that mean strong or weak IMFs? Right? We don't have to put much energy in to break those apart. They're ready to go, right? So by lowest boiling point, that's code for the weakest intermolecular forces. And by the highest boiling point, that's going to be code for the strongest intermolecular forces. So what we need to do is we need to look at these structures and identify these structural features that correspond to our different IMFs. All right, let's take them one at a time here. This molecule containing only carbons and hydrogens would be considered what? Polar or nonpolar? Anything that's only carbons and hydrogens. Carbon and hydrogen, even though they are kind of separate, far apart on the periodic table, they have the same electronegativity, right? So these are not polar bonds here. So any molecule that consists only of carbons and hydrogens would be nonpolar. And if it's nonpolar, what are the strongest intermolecular forces that it can have with neighboring molecules? Those very weak dispersion forces. Okay. If we look at our other two molecules here, these are both polar. We got these polar bonds here. All right, but one of these has that very special type of bond in it so that it can't just dipole-dipole interact, but it can make those even stronger hydrogen bonding interactions. Which one is that? The one on the left or the one on the right? Both of these have hydrogens, right? Importantly, you have to be one of these special bonds, either an oxygen bound to a hydrogen, a nitrogen bound to a hydrogen, or a fluorine bound to a hydrogen. Again, our very small, very electronegative elements. Look where nitrogen, oxygen, and fluorine live on the periodic table. Those are the only ones that can hydrogen bond. So if you don't have one of those here, this carbon-hydrogen bond, that's not going to cut it, right? So this one can hydrogen bond. My other molecule's polar, but it doesn't have one of those three special bonds. So the only thing it can do is dipole-dipole interact. All right, so I'm going to try to rank these from the weakest intermolecular interactions to the strongest intermolecular interactions. Which one's going to be the weakest? My dispersion forces. So my lowest boiling point would be this molecule here. What about my highest boiling point, my strongest intermolecular interactions? Those hydrogen bonding. So clearly I was very creative drawing these molecules in the exact order that they were going to be ranked in. All right, but yes, if we're going to rank them from lowest to highest boiling point, we have to look for these structural features that correspond to those intermolecular forces and rank them accordingly. All right, let's do another example here. We're going to play the same game where we want to rank from lowest to highest boiling point. so first of all, just FYI, when you get to a certain level of chemistry, there's this like shorthand for drawing structures that's way simpler than these Lewis structures. It's kind of a pain in the butt to draw Lewis structures for larger molecules, but this is all we know at this point, so we're going to draw our Lewis structures here. And we notice that all of these molecules are what? Polar or nonpolar? They all only consist of carbons and hydrogens. There are no polar bonds in any of these molecules. So these are all nonpolar. Which means they all only have those very weak dispersion forces available. So then how the heck am I supposed to know what the ranking's going to be here? How do I tell which one's the strongest dispersion forces versus the weakest dispersion forces? All right. Well, remember at the very beginning we talked about dispersion forces in particular and how they increase with the increasing surface area of a molecule. So what does that mean? That means that larger molecules have more surface area, and thus larger molecules will have stronger dispersion forces than smaller molecules. There's just more atoms that can interact in a larger molecule, right? So we said that this is going to increase with increasing surface area. That simply means that our larger molecules have stronger dispersion forces. So in the first example, we were comparing molecules that were all about the same size, but they had these different functional groups, these different intermolecular interactions available to them. Now we're looking at molecules that are all got the same type of intermolecular interaction, these dispersion forces, but we can still rank them from lowest to highest boiling point because they differ in their size. The larger molecule will have the strongest dispersion forces, and the smallest molecule will have the weakest. Oh, that middle guy's in the middle there. All right, so the strength of these dispersion forces is going to increase as the size of our molecule increases. All right, one more here. Again, we're going to rank these from the lowest to the highest boiling point, which again, by boiling point, we're code for our intermolecular forces. All right, so just to be clear, if we're going to play like the spot the difference game here, these all differ because I've stuck a different halogen on that carbon. All right, so first of all, are these molecules polar or non-polar? These ones would be polar. We got this polar bond. Those halogens are fairly electronegative compared to carbon. So these are all polar molecules. Can they hydrogen bond or only dipole-dipole? Right, remember to be hydrogen bonding, you have to have one of these three specific bonds going on in that molecule. Fluorine hydrogen, oxygen hydrogen, or nitrogen hydrogen. None of these contain one of those three special bonds. So they can't hydrogen bond, but they're polar. That means that they can dipole-dipole. Okay? All right, and it turns out that the strength of that dipole-dipole interaction will be a little stronger in this middle one because it's chlorine, which is closer to fluorine. All right, but the important difference here actually is going to correspond to the dispersion forces in these molecules. Remember, even though these are polar molecules and they can dipole-dipole interact, everything has dispersion forces. All of these can dipole-dipole interact. So what's the difference between them is that increasing atomic number. Those larger atoms can form much stronger dispersion forces than those smaller atoms. So since the dipole-dipole interactions are about equal in those three molecules, the difference here is going to come from that increasing atomic number in our halogen here. All right, so the highest boiling point is going to be this large iodine here, where the lowest boiling point is going to come from our smallest halogen, our chlorine. And bromine sitting in the middle is going to have that intermediate boiling point. All right, so again, ranking from our lowest boiling point, the smallest atom here, chlorine, to our largest, the most electrons in that iodine atom. Okay, so again, we talked about these phase changes. Why is this relevant to this discussion of intermolecular forces? Because it's a really easy way to measure the strength of those intermolecular forces. Right? Measuring the melting point of a solid is something that you can do in approximately 4 minutes in the lab. Very, very easy to do, right? And it's a stand-in for just how strong those intermolecular forces are in that molecule. Likewise, if instead we started with a liquid, we could measure its boiling point very easily. And again, just a stand-in for how strong those interactions are between neighboring molecules in that substance. All right, we're going to talk a little bit more about solids here. Okay, and we've talked about how we got two different types of compounds. This goes back to the very beginning of the course when we were talking first about nomenclature and being able to look at a compound's formula and identify whether we were looking at an ionic or a covalent compound. If I have an ionic compound, so for example, NaCl, how do I know that that is ionic? Just by looking at that molecular formula. As opposed to, for example, CO2, which would be not a, well, that's not a solid, so I guess that's not going to work out. We can talk about ice, H2O, not a ionic compound, but a covalent compound. So what did I look for in these two formulas that told me what these were, ionic or covalent? In an ionic compound, where does sodium live on the periodic table? All the way on the metals side. And where does chlorine live on the periodic table? The nonmetals. So absolutely, our ionic compounds are metals and nonmetals, whereas molecular compounds are only nonmetals. Okay? If we look at the structure of these ionic compounds, of these ionic solids, right, they are just repeating arrays of positive and negative charge. So for example, in sodium chloride, my sodium ion has that positive charge because it's got one more proton than it has electrons. And likewise, my chloride ion has a negative charge because it has an extra electron, right? And these opposites attract. So when these compounds form, when these solids form, they're just repeating arrays of positive, negative, going in all directions here, right? So we have those opposites attract interactions going on, okay? So importantly, in an ionic solid, what's holding that solid together are those ionic bonds. We talked about these intermolecular forces. An ionic bond, a bond is way stronger than just interactions between neighboring molecules, than, for example, a hydrogen bonding interaction. So these ionic bonds are very strong interactions. All right, if I was going to rank these, we said it was dispersion, dipole-dipole, hydrogen bonding, ion-dipole. All the way over there would be these ionic bond interactions, much stronger than any of those intermolecular forces. Now we have full opposites interact, electrostatic forces going on here. Okay? Because of that, because there are these insanely strong forces holding these solids together, what would we expect about their boiling point? Do they have, their melting point? Do they have low melting points or high melting points? Super high melting points, all right? So because they're held by these ridiculously strong interactions, these have super high melting points. All right, so much so that you do not encounter liquid ionic compounds, right? You have to be at a ridiculously high temperature to do that. The only time practically that you ever encounter an ionic compound in its liquid state is down in the very core of our planet. That molten lava contains those melted ionic compounds, all right? But if you're not lava hot, you are not hot enough to melt an ionic compound, right? Ridiculously high melting points for ionic solids. Okay, and then lastly about these ionic compounds, which is almost counterintuitive because we're talking about how strong these interactions are. They're also considered to be very brittle. So they break or crack under force. And that might seem counterintuitive, but let's think about this here. Let's again picture our ionic solid. We're going to do these repeating arrays of positive charges and negative charges. I'm going to use this same coloring scheme from the previous slide. Okay, and we don't just have two, we have a whole bunch of them lined up in every direction here. All right, and then my next layer is going to be staggered so that positive charges are all surrounded by negative charges, and negative charges are all surrounded by positive charges. Okay, so here's my ionic solid here. And now I'm going to take this thing and I'm going to whack it with a hammer. All right, we're going to impart this force on it here. And what's going to happen? Okay, so what that force is going to do is shift these ions just ever so slightly down here, right? That force messed up this solid and now rearranged it. And my problem is now I have not my very nice opposites interact favorably interaction. I have instead these like charges repelling one another, right? When you shift around this structure ever so slightly, now I have positive charges next to positive charges and negative charges next to negative charges, right? Like charges do not like being next to one another, so what this thing would do is it would just crack at that point, right? You impart this force and shift everything ever so slightly, that's going to lead to this crack in our structure here. I guess we could do it like this. Right? This gets shifted down and ends up cracking because now we have our like charges repelling one another. Okay? So it's not easy to do. I'm not saying you don't have to impart a large amount of force on it, but you don't just sort of like dent it, you'll actually crack the structure. They're considered to be brittle. A great example of ionic compounds that we see are rocks, okay? If you've ever had to dig up, dig a fence post in a rocky area, you're gonna use a jackhammer. It's not easy to do, but when you do take a jackhammer to a rock, it cracks it open. You don't dent the rock, right? So same sort of idea here. Our ionic compounds, they're quite strong in how they're held together, but any slight change in that structure will lead to a crack, will lead to this fault line. Okay, so now let's talk about molecular solids here, or covalent compounds, which consist only of nonmetals. All right? If we look at the structure of, for example, ice, let's see if we can simplify this a little bit. There's a little bit too much going on here. Okay? We're going to focus here. Here's one of my water molecules. Okay, I have this covalent bond between my oxygen and my hydrogens. And then here's a neighboring water molecule over here, consisting of those same covalent bonds. But importantly, in this molecular solid, in my structure of ice here, neighboring water molecules are not covalently bound to one another. They're interacting between the partial positive hydrogen of one water molecule and the partial negative end of that oxygen on its neighboring water molecule, what we call hydrogen bonding. All right, so our forces in a covalent solid that's holding that solid together are not the covalent bonds. Those exist within a molecule, right? But neighboring water molecules are bound together in that ice molecule through those intermolecular forces. All right? So our solid is held together by those intermolecular forces that we discussed. Right? Exactly which intermolecular forces are going to depend on what covalent compound you're talking about. All right? In the case of ice, it's that hydrogen bonding interaction. But these are these intermolecular forces, which we said were way weaker than our ionic bonds. Okay? So because of that, these are not as strong of interactions. Compared to those ionic bonds. So whereas ionic compounds have those super high melting points, covalent compounds have lower melting points. Because you're not breaking an ionic bond, you're only breaking those intermolecular forces. All right, we can say that ionic compounds are brittle because they all have the same basic structure. Covalent compounds, way more complicated. The properties of covalent compounds vary quite a bit depending on what molecule you're talking about. So we're not going to make any sort of broad statement about our covalent compounds. All right, importantly though, these intermolecular forces that are holding that solid together are one of those four that we talked about, or one of those three actually that we talked about, either dispersion, dipole-dipole, or hydrogen bonding. Can't be ion dipole because you can't have any ions in a covalent compound. All right, and then the last type of structure, the last type of solid that we're going to talk about, which is going to be kind of new, we haven't really discussed these, are what are called metallic solids. Okay, whereas ionic are metals and nonmetals, and covalents are all nonmetals. What do we think metallic solids are going to be? The metals, right? So these are solids that consist of only our metallic or our metal elements. All right, and so you can have a metal all by itself. So for example, you could have pure copper, but there are also other metals out there that are a mixture of two different elements. So for example, brass is a mixture of copper and zinc. These two metals, you kind of mash them together and you get this new metallic solid. All right, that was a big point in history, was when they realized that they could make all these different metals, and we had, the Bronze Age and whatever the crap, right? They built stronger and stronger weapons when they realized they could make stronger and stronger metals. All right, and so the important difference here is how we think about how these metals are being held together. All right, so importantly here, let's take a look at this metallic structure here. So each one of these we're going to say is a metal atom. So for example, an iron atom. All right, what's important to remember about metals, we discussed this when we talked about ionization energy. Metals, the amount of energy you have to put in to get rid of an electron. Metals, you don't have to put much energy in at all, because metals do not hold on to their electrons very tightly. Okay, so in this solid here, we have each one of these iron atoms. Each iron atom has a bunch of electrons. So we got a bunch of electrons here. All right? But these electrons, these metals don't hold on to these electrons very tightly. So these electrons aren't going to stay fixed in one position. They're going to be able to freely move all the way around this structure here. All right? This is what we call, so our model for bonding in a metallic substance is what's called the sea of electrons model. All right? The idea that these electrons aren't being held very tightly, they're able to dissociate or to delocalize throughout that entire structure, creating this sea of electrons that those positive charges are just floating around in. All right, so our metallic bonding model we call the sea of electron model. The idea that all these electrons, between each one of these nuclei, we have a bunch of electrons just freely flowing around. Okay, so we're going to define this sea of electrons model here. Our protons are quote-unquote floating in a sea of electrons. My protons are floating around in this sea of electrons. The electrons are like the water, and the protons are there kind of sitting in that sea of electrons. Right? The electrons are the ones moving freely about, and our protons are floating around in there. Because of this, metals have this property that's very distinct from ionic compounds or covalent compounds, which is that they can conduct electricity. All right, there's a reason why we make all of our wires out of metals, because we can easily pass electrons through that solid substance. All right, conducting electricity is just a fancy way of saying electrons can move freely. To be clear, electricity is electrons, right? When we're running electricity through a light bulb, what we're doing is running electrons through that light bulb. All right, and then the last property of these metallic substances that we're going to note here is that unlike our ionic compounds, these are not considered to be brittle, but rather malleable. They will dent under force, not break. All right, and that is why we use metals so often in sort of construction and engineering, or even way back in the day when they were just using it to make better and better weapons, because you could sit there and you can manipulate that material without actually breaking it, right? We can create it, dent it into this nice sharp edge without actually breaking that sword in half. So metals are considered to be malleable, meaning that they dent under force instead of cracking. Cool. All right, we're going to pick this up next time, and we're going to and then we're going to talk about liquids and the various interactions that we see in liquid structures. Say it again?
The final exam will be in this room, right?
The final is what?
Exam will be in this room.
Yes, correct.
Okay.
Yep.
Thank you.
Do you want candy?
No, I'm good. Thank you, though. I appreciate it.
Are you going to Vintage Days?
To what?
Vintage Days?
I don't know what that is.
Apparently it's a big event Fresno State has.
Oh, no.
I don't know.
I did not get the memo.
I just found it out. Apparently there's going to be like a math contest.
A math contest?
I know. It sounds exciting. But
That would be cool if I was as brushed up on my math skills as I should be.
you know, apparently there's also going to be a CSM event and the Vintage Days, and everybody else is just going to join because the traffic's going to be there.
Cool.
Might spend some money. Apparently there's even like an anime vendor that's going to be here.
Oh, cool.
What?
Here we go.
Is that our password?
No, sorry. Um, yes, so yes, it should completely transfer. The only thing that you would need to be careful for is certain degrees require like certain lab hours. So really the sort of caveat that I would say is like, so for example, there's a course 3B that you can take that has a lecture and a lab component, but you have to do the lab in person to be able to have it transfer to a dental school. So there's certain, like, the university, Fresno State might accept it as whatever, but then your degree program might have a stipulation about in-person versus online. That'd be the only caveat.
I'm not too worried because it wasn't required for my career.
Then yeah, I wouldn't worry about it, yeah.
And it's math.
Okay.
It doesn't have a lab.
Yeah, okay, cool. Yeah, that doesn't sound like a problem. If it does, as long as it does, as long as you know that it's accredited and transfers, then yes.
I make sure that their Cal 2 on this community college transfer directly through Fresno State as Cal 2.
Yeah,
So on this program, it shows that it's
so you should be fine.
okay.
Yep.
I was just worried that because it's like completely online.
Yeah.
No, there's no Cal. That's all they offer.
Yeah, no, when they made it online, they would have had to have made that course like accredited, so it was the same equivalent as to the in-person one, basically.
Okay, so thank you.
Yeah.